Let's deal with a new topic, that is crystal field theory. Crystal field theory was developed in 1930s and it is applied to transition metals in crystal lattice, and so it is known as crystal field theory. In crystal field theory, in the formation of a coordination complex or in a coordination complex, the relationship between the central metal ion and the ligands are considered as purely electrostatic, and the charge in the central metal ion is its oxidation state, and then the ligands are approaching the central metal ion with its pair of electrons, and in case of neutral molecules like ammonia, its dipole, it is actually existing as a dipole and its negative end is pointed towards the charged cation in the central metal ion. When the ligand approaches the central metal ion with its pair of electrons or with its negative charge, these electrons in this metal ion feel a kind of repulsion, and so these electrons in the outermost d orbital of this metal ion will try to occupy at the farthest end of the d orbital to avoid repulsion maximum from the approaching ligands. So we will see, this is the basic principle regarding the crystal field theory, and then we will see a frequently asked question, that is, explain the crystal field splitting in an octahedral complex. It is a frequently asked question in the board exams. Let's see. This is the structure of the alignment of metal ions and the ligands around the metal ion, central metal ion in an octahedral complex. You know that 6 ligands are approaching the metal ion in an octahedral complex. You can see here in an octahedral complex, the central metal ion is here and ligands are approaching at the 6 corners of this octahedron. Directions X, Y and Z pointing at the adjacent sides of that particular octahedron. And then here we have these 6 ligands approaching in X minus X, Y minus Y, Z minus Z directions. That in crystal field splitting or in the formation of a coordination complex, we are dealing with transition metal ions. So its outermost orbital is always a d orbital. And what is the speciality of d orbitals? They are degenerate orbitals. They are orbitals with the same energy. All those 5 orbitals in that d orbital will have the same energy. And what happens during crystal field splitting is, these orbitals with same energy will split up and forms 2 different sets of orbitals with a different energy. These are the 5 orbitals: dxy, dxz, dyz, dx square y square and dz square. These are the 5 sets of orbitals that you have seen here. These 5 sets of orbitals are currently, that is before the formation of the coordination compound or before this crystal field splitting is happening, they are with the same energy. And this thing is very important. This dx square, y square and dz square is placed or it is situated along the axis, and dxy, dxz and dyz is placed in between the axis. So we have here we have dx square, y square and dz square, and these orbitals we call as Eg set of orbitals, and then dxy, dxz, dyz we call it as T2g set of orbitals, and here these dx square, y square and dz square lobes of this d orbitals are pointing along the axis. Okay, and this dxy, dxz, dyz are situated in between the axis. That is the main point in this. When a coordination complex, an octahedral coordination complex is formed, what happens is the ligands are approaching along the axis. That means the ligands are approaching the Eg set of orbitals, and you know that ligands are coming with its negative charge, pair of electrons with it, and in the d orbital we have, in the metal ion we have that same negative charge because of the presence of electrons. So they feel a kind of strong repulsion. Who feel the maximum repulsion? Or those orbitals, those electrons in the orbitals which are along the axis, they feel maximum repulsion in the case of octahedral complexes because the ligands are approaching along the axis. And so this Eg ligands. And T2G feels a less kind of repulsion because they are not situated along the axis, but they are situated in between the axis. So they don't feel that much kind of repulsion from the approaching ligands. And so what happens? These two set of orbitals will split up and they will form as a two different set of orbitals, and that is known as crystal field splitting. Okay, that's all about the crystal field splitting in octahedral complex. I hope you have understood. Thank you. We'll see you again.